Hello, my name is Dylan Whitehead, and I'm currently a senior majoring in computer science over at Edinboro University. Today I'd like to take some time to talk about the skills that are necessary for independent 3D game development, how those skills are necessary for working in a game studio, and how those skills apply to a more traditional software engineering environment. So over the past year or so, I've been developing this project along with the help of some talented friends and some of the wonderful professors over at Edinboro University. The project was designed as a proof-of-concept 3D racing game inspired by anti-gravity racers from the 90s and 2000s like F-Zero and Wipeout. What was important in this project was being able to accurately recreate the physics of these games in a newer engine from scratch, as well as making something that is modular enough so that further development can continue if the project were to proceed with full development. The development process for this prototype has taken around a year off and on, of programming and different asset creation. Everything that you see here was made specifically for this project. There were no bought assets or anything like that, and all the physics are being computed using the algorithms we developed as opposed to using plug-and-play libraries or default engine systems. The project was developed on Unreal Engine 4, which I would highly recommend for 3D game development as it's free and has quickly become one of the most popular engines used in the industry. The project was coded primarily using C++, as well as additional programming being done with Unreal Blueprints. As of now, the game is a time attack style mode where users can compete on 3 different tracks with 3 different cars to see who has the best times. Like I was saying, all the translations, rotations, and scaling and collision that you're seeing now are computed using custom code that was developed using the tools and practices taught at Edinboro University as part of their computer science program. So what I'd like to talk about today is the tool set that was required for a project like this to get developed, as well as how that tool set is relevant to positions found in the software engineering industry. We're going to be talking about the design process and how game design relates to the classic design phase of the traditional software development lifecycle. We'll talk about programming, of course, both in a more general sense and also more specifically with good programming practices and principles that made a project like this possible. Mathematics, again a little self-explanatory. Don't worry if you're scared of math, I was too. I promise it's not as scary as it looks. But also we'd like to focus on communication and creative problem solving. Being able to effectively voice your ideas, hear criticism and feedback, and take that into account as you're working on and throughout a project. First, I'd like to make sure everybody is on the same page as to what I mean when I talk about game development, since the term is used pretty liberally by different people to describe several different things. Game development is many, many careers bundled together. In a studio environment, a lot of uniquely talented people will collaborate without overlap. I think this is what can confuse some people up when they're looking to learn more about game development. You don't go to college necessarily to become a game developer, because game development isn't one singular thing. It's many things that are required to get to a finished product. There are designers who create how the experience of the game is going to feel and try to outline the overall user experience. There are artists who decide on character designs and the look of the game. There are software programmers who develop the game's systems and mechanics. There are hardware programmers who develop and maintain the engines these games run on, and many, many more things that go into any game. Software engineering is a sought-after position in game development studios, required for developing both studio and independent computer games, though due to the different environment from a traditional software studio one, it's often classed as a separate career. When I speak about game development going forward, I'm mostly referring to the designing and programming of the game software and its mechanics, not so much the other necessary work that goes into a title before launch. So where better to start than the design phase? My favorite part, a sentiment that I'm usually alone on. One of those necessary skills I was referring to is being able to design something effectively and efficiently. Design, at its heart, is really the process of taking a good, hard look at something and describing everything you can about it. Say we want to take a book and simulate it in a computerized window. Your first reaction may be to describe the book literally. Recreate the title, the number of pages, how big the book is, and the content. But it's also more than that. It's about really getting deep in the details of what's necessary for conveying that this thing we are looking at on the screen is indeed a book. Maybe that includes the texture of the paper when you feel it as you turn the page. Maybe that's the sound it makes when it hits the ground from a tall bookshelf. Maybe it's the little imperfections of the printing press it came off of on the font. Whatever helps to sell to the user that this is a book is part of designing that system. So, you collect all those necessary details, and you look at them from an engineer's point of view. How are we going to build this? How many different functions will we need? What kind of class libraries will be used? How is this book going to interact with other objects in our program? How many ways can the book be interacted with? What kind of hardware will the user need? It's about defining the problem. In this case, how do I convince somebody that this is a book? And then defining the process you are going to use to achieve that result. That's really the center of good design. Often these projects deal with a lot of interconnected objects and systems, and having a straightforward plan set beforehand is incredibly important for finishing a project by a reasonable deadline. Trust me when I say, you do not want to be that guy who is working on a piece of software when a deadline is coming up and there's no plan for how to finish it. So, design documents and who needs them. A design document is really what you'd think it is. It's the beginning blueprint for software. Really, even if you're just dabbling in software development, you should be designing what you want to code before you code it. Everybody benefits from a solidly designed foundation, as it makes the process of moving to programming that much easier. Getting into that rhythm of designing something first and then translating that design to a coding language later is a great start for developing this skill. I've compiled a couple of cool game design documents that have somehow found their way out of a non-disclosure agreement, so let's take a look. Here we can see an example of a game design document that was used for the game BioShock, if anybody remembers it. One of my personal favorites. This one is referenced very heavily by different game development articles to illustrate how to properly structure a design document such as this, since for a while it really followed the industry standard. Nowadays, design documents tend to be less paper-based and be more like a custom wiki page that developers get access to, so that way they can better keep track of version history and updates. Still, this is a great resource for what to include in a game design. This is from the original Diablo. This is a real oldie, but it's referenced by a lot of game developers still due to the content included. Here's a cool snippet from a Halo 3 design document that detailed matchmaking functionality and the different UIs that they would be using. As you can see, it showcases the different relationships and navigating between the different screens. Diagrams like these are used all of the time for painting a better picture of how exactly a program is going to function during runtime. I'm sure if you go into computer science, you'll learn to hate the term ER or UML, but they really are very useful. And here's some stuff that went along with our project's design phase. On the left is one of the earliest agreed on designs for the different components of our ship actors. Don't mind the crude napkin drawing, I promise it looks more official in the final project. Then we have the design document that took entirely too long to finish. Then we also have some early art that was used for better conceptualizing the characters and tone. Keep in mind, all of these things go through constant revision before any kind of finalization is done. The goal is to create a blueprint so that the programming phase is nothing more than translating from English to whatever coding language is used. But the design phase is long, and it takes a lot of iterations before being ready for that next step. Important to note here is that game design documents are more often about the intended user experience than an instruction on how to create something, though a lot of the time they are accompanied later by a more technical design document that details that. Pretty much every game you've ever played was typed out in dreadfully boring detail way before you ever got a chance to play it. The design phase is more than just detailing what you want the program to look like, however. Writing algorithms, detailing frame rate and intended hardware specifications, laying out class diagrams and intended functionality. All of this is a major part of designing a software project. This level of detail in the design helps avoid problems later down the line. For example, in our project, we knew early on that using Euler angles for our ship's rotation wasn't going to work because of gimbal lock. It was incredibly important early on to get a solid grasp of how we were going to structure our system around quaternion geometry to avoid this problem. Otherwise, we'd have to massively backtrack to resolve this issue. Now, that's obviously a very specific example, but even in a broader sense, laying out exactly what actors we needed, how their class hierarchies worked, and their relationships to each other ahead of time was integral to making sure that we didn't lose a lot of time later having to go back and adjusting the entire project just because we didn't plan for a specific scenario. How does this relate to traditional software engineering? So as I was saying before, game design documents are often more about the user experience, whereas software design documents are more about the how and how much. Depending on the software development cycle being used, the first to be made is the requirement specification sheet, which details the various main behavior of the software systems, as well as relationships, dependencies, and so on. That doesn't mean they're totally unrelated. Both require a similar skill, which is being able to appropriately plan out and diagram an intended purpose. I'd say even being able to design everyday objects, like a wallet or a handbag, is a great indication of this skill. It's about being able to visualize a result and then getting there in a manageable and efficient way. Optimizing an algorithm like that for better runtime or less overhead saves the company a lot of headaches down the line. So let's talk about some of the programming principles that were used during the creation of this project. This is only scratching the surface of good programming principles. It really takes a lot of time commitment and practice to understand them fully, but I'd like to introduce some of the more useful ones just to get those terms floating around. The first principle I'd like to talk about is abstraction. Abstraction is the process of removing all but the most important details used to describe an object. What this is essentially saying is that when we create data structures, that we should be mindful of what the important part of our code is, and to design our systems in such a way that they are easily and quickly used and understood by others. As systems become more complex, abstraction is a constant necessity for being able to work efficiently. One example of abstracted objects in our project would be the controller hardware. It's not necessary for our purposes to understand exactly how the supported controller hardware functions. It's just about being able to use it properly such that any input it receives gives a predictable output. The goal is to design any custom data structures in a similar way. For instance, in our project, a simple track class was made using spline meshes that allows anybody in the editor to simply place the object in the world and quickly add and manipulate track segments to make a completed track. This saved time in development later down the line and made making custom geometry much easier. More importantly, however, it allowed a way of interacting with the track editor in such a way that whoever was using it wasn't required to know how it works, just how to use it. Being able to do this in a traditional software engineering environment is vital, as well as it ensures that when you are working on a data structure, wherever it goes, it is easily used and fits to the rest of the system. Up next is encapsulation. Encapsulation is the process of melding together all the data and behavior that comprise an object to a single source. What this is saying is that we should design our objects in such a way that there are as few definitions needed as possible for that object. For instance, in this project, for our ships, instead of having our code that define the behavior of this ship strewn about the project file, all of it is centralized in a singular class file that quickly defines what it is a ship is and what it can do in our game. If you were in a traditional software engineering studio and you weren't encapsulating objects, you'd be in a lot of trouble. It's important to keep a clean and easy-to-use container for your implementation so that it doesn't interfere with other systems and doesn't become too difficult to trace later when debugging. Modularity is an extension of this idea. Modularity is this idea that objects should have as few dependencies as possible on each other, and that we should design our classes in a way that can be easily replaced without affecting the overall system. There are going to be times where this isn't totally possible, and you have to just try your best. But it's applicable in a lot of scenarios, and it's more of an idea for what to strive for than an absolute law. For instance, when designing how the collision detection would work in the 3D world of this game, a lot of care was taken in trying to make sure the necessary connections between objects were as few and far between as possible. When looking at this problem for the first time, your gut instinct might be that to determine how an object collides with another object, it needs to know everything about how that other object works. After all, a falling bowling ball collides with a soft carpeted floor a lot differently than it does with, say, a glass table. It's not the case, however, since we can bring down our necessary connections substantially by just separating our types of collisions into groups. Then, maybe we could add a flag to every object we create that will then detail what group it's a part of. After that, we can look through these groups only when they're applicable, reducing our number of checks and therefore number of dependencies. That alone takes us from every object needing to know about an infinitely many number of objects to just a handful of different values that we can define ourselves. We can then take this even further and have a way of describing if an object has any collision at all, reducing our number of checks once again. This way, if we decide to add a new object, or delete an existing one, the amount of work we must do to make our previous work function is drastically decreased, which saves us time, which is in turn saving somebody on development budget. Inheritance. Inheritance is the process of sharing data and behavior of a class to another class through a hierarchical structure. What this means is we want to design our classes in such a way that we create a vague class first that defines behavior that many things share, which we call a parent, and derive classes from that parent named children who gain that behavior but can take it further and make it more specific. To better visualize this, let's say we want to map out the functionality of a couple of kitchen appliances. We know we want to detail a microwave, a blender, and a toaster. One way is to describe each individual one as we look through them. So, we painstakingly write out every detail about each of these objects individually, how they work, how they look, and how we want them to be used. The problem with this approach is that there's going to be some overlap every item. For instance, we already know each of those objects has an electrical cable. We just don't know what the wattage is, if it has 2 prongs or 3, or the type of wiring. We know each one is made of mostly metal with a plastic case around it, just not the ratio or the shape. Using inheritance allows us to describe these things a single time and share that description among different objects. So first we define what an appliance is. This is where we put everything that every appliance in our kitchen is going to share. Then, we define our individual appliances, keeping in mind that we don't have to restate what an appliance is. After all, we just defined it. This saves a lot of time. For this project, we define what an actor is. An actor is something that we can place in the world. It can accept and change components, it has a collision channel, and it appears in the editor. Then, we define what a ship is, how it moves, how it acts under certain conditions, that sort of thing. Our ship is also then defined as being something that can receive input and output a predictable result based on that input. After that, we define specific ships. One's fast but has slow acceleration, or this one is slow but has good turning. This one has 4 particle systems attached, whereas this one only has 2. That's the true strength of using inheritance. Since we previously defined certain characteristics that multiple things share, we don't have to keep repeating ourselves. We can just refer to our previous definition and tell our compiler, hey, this is one of those things. Please treat it like one. Another important skill I'd like to emphasize is just how important different mathematics were in this project. An understanding of trigonometry was necessary for different collision computations, as well as being able to predict and manipulate different rotations during runtime. Linear algebra is everywhere in a 3D engine, and understanding how transformation matrices function was necessary for setting things like translations, rotations, and scaling of the different objects as they interpolated through different values, since they had to be done in a specific order. Discrete mathematics is also very useful for being able to properly develop algorithms as well as debug any issues that may arise. While a lot of specific mathematics were useful for this project and are incredibly important for software development, what I'd really like to stress is the other strength of math. I'm not somebody who ever considered themselves good at math, but in software environments, it's not necessarily about who is best at memorizing specific equations or processes. The real strength of learning different mathematics in terms of software is being able to work your way through and understand a system of logic. Trust me, nobody hated trigonometry more than me. I was the grand champion of hating math at one point. But don't view it as learning things that are going to be directly applicable in your future career. Treat it as learning how to better identify relationships between identities and practicing your ability to understand overall concepts in an effective and quick way. Developing that skill of learning a set of logical rules and their limitations and working your way through it is incredibly useful for programming, so that's pretty much all you're going to be doing. In both game development and traditional software engineering, you're going to get a library of definitions and methods, or an engine with a set of libraries, or a coding environment with a UI that shortcuts different library functionality. And you're going to need to be able to read through the documentation of those things, understand the logic of the different data structures, and make them work best for you. The easier you can do that, the better. What's important is that this skill especially takes a lot of time to develop and isn't one that is readily apparent when it's improving. Only much later down the line can you see that you've improved. This way of thinking was the only way this project was possible. Working in a 3D engine as large as Unreal is a lot to take in. As a result, it can feel incredibly intimidating. What got myself and others through, however, was the ability to look for what you understand and expand upon it. The more you've practiced at understanding a system of logic, the faster this expansion is going to happen. I really can't stress enough just how useful of a skill this is for game development and software engineering as a whole. This is also a good time to mention how useful a knowledge of computer graphics can be when developing games. Being able to properly understand how shaders and lighting are being displayed on a screen is useful for setting up a scene, as well as manipulating the geometry of different objects for desired effects. It's also a great way to better understand things like perspective and cameras, as well as things like FOV and frame rate. While it may not be your intended area of expertise, it's a useful topic to understand such that when you collaborate with others in the field and request for things to look a specific way, you don't make impossible requests. Here you can see what our project looks like with only the wireframe outlines of our actors being displayed. Understanding how the engine treated things like rendering face and vertex normals was vital for being able to program the way our ship rotated around the track to get that anti-gravity look to it. That brings us to communication. Proper communication is a necessary skill for developers in any kind of career environment. In software, being able to properly talk through your ideas, trace your algorithms, and collaborate with others is completely crucial for a project to get finished by a certain deadline. If you're like me, or if you're pursuing computer science in general, chances are you're an introverted person, so this step is going to be kind of difficult. What's important is that you make that effort. While it may not initially seem like it, game development is a lot of work. It's really crying out for collaboration, and if you try to do everything yourself, you're going to get burnt out very quickly. I've had it happen to me, I've seen others be affected, it's just too much work to do by yourself. The other thing is that criticism is really the only way you're going to grow, and is a great way to learn. If you're sitting on your own working on a project without answering to somebody, chances are you're going to eventually let yourself take shortcuts or compromises that other people would otherwise tell you don't look right. The other thing is that in a lot of situations, people don't know what it is that they're really asking for. If you're in a studio working on code and your boss tells you that he wants flashing buttons on the screen, chances are he doesn't know how that's going to affect the rest of the system. He just wants things to look a certain way. That's where proper communication must occur, and you need to come to a better agreement on how you should go about working on it before you waste a whole bunch of time. Ultimately, that's really what a lot of these skills and practices come down to. You can be the best, most knowledgeable programmer in the world, but if you can't properly manage your time and use it efficiently, you're just not going to get anything done. This type of work is far too time-consuming to be wasting it on work that is redundant. If it weren't for proper communication, this project never would have left the earliest phases, as I never would have been pushed by peers to pursue it further. Something else to keep in mind when working on projects like these that is unavoidable is that you must be good at solving problems in creative ways. There's going to be times where you hit a roadblock and you are stuck working on the same thing over and over, or you know something is coming up that is going to be a large time sink. In those situations, being able to think outside of the box and come up with a better strategy for tackling those issues is a great way to save unnecessary effort that could be put into more important things. Again, in those scenarios, it's not necessarily about how knowledgeable you are or how much experience you have. It's about your ability to use that part of your brain to come up with alternative routes through a maze, come to a novel solution to otherwise ordinary issues. Sometimes this means taking advantage of some side effects of a system, or using a tool in a supported, albeit unusual way. And if it makes the process go faster, and you can properly explain your way through it, then it can really save you some time during development. Finally, I'd really like to put an emphasis on iteration, what it meant for this project, and how helpful it can be to anybody in the software engineering industry. This project started out looking like the above picture. The rotational geometry had major issues with gimbal lock because our algorithms weren't taking it into account yet. Our assets had bad UVs, so lighting and textures were poor and stretched, and the physics were having unintended side effects that made movement jerky and strange. What we could have done is stuck to the project at hand. Try to repair those bugs, and do our best to patch the algorithms to become more in line with our intended behavior. What we instead did, which is what I'd recommend everybody do if they are struggling to fit a square peg into a round hole, is to take a step back, gather the knowledge you've learned from the experience so far, and start fresh. Each of these different pictures represents a different prototype, with different class structures, different algorithms, and different computations being made. What's amazing about this skill set, though, is that it constantly builds on top of itself. So yes, you are restarting from scratch, but you're no longer in the same position you were in the last time you started. You're going to be able to start again faster, with a better idea of the problems you'll be facing, and have a much larger internal database of what tools you have at your disposal and how they apply to situations moving forward. This applies to a large-scale problem, like working on a project, to even just a small-scale problem, like an algorithm or a function that you're trying to design or program. While it may initially feel like a step backwards, the feeling you get when you're making it further than you did the last time, at a faster pace, is incredible, and you'd be surprised what you can create when presented with a fresh perspective. So that concludes what I had wanted to discuss today. I really hope I was able to show some of you the strength of certain skills as they relate to both a game development studio and a more traditional software environment, as well as the usefulness of some of the different techniques that were used during the creation of this project. Like I had mentioned, everything that was discussed was completely necessary for this project getting finished at a reasonable deadline, and was taught as part of the great track over at Edinboro University. Thank you for allowing me to show off my project. It was a lot of fun to design and develop, and I got the chance to work with some truly talented and incredible people, which is something I won't be taking for granted anytime soon. If you are interested further, I'm proud to be able to say the project is fully playable on PC and ready to download. Thank you.